Yes, sir. Recording started, sir.
Yeah. Welcome for the session on how the processor is designed with a single bus and a multiple buses. So in this session, having the knowledge of assembly language and having the knowledge of assembly instructions, we will analyze how given any machine level language instruction is getting executed by the different hardware blocks present inside the processor. So the outcome of this session is, at the end of this session, you must be in a position to understand if the instruction is given in binary language, let's say machine level language, how that instruction we can fetch into the processor, how that instruction is getting executed by different digital systems or blocks, what is present inside the processor. So before we start doing that one, let's analyze what is present inside the processor with a little more understanding. So look at the connection between the processor and the memory. The address k bits decides how much of memory you can have in your system. That is up to the power of k is the size of the memory what we can have it. Whenever processor wants to read or write from the memory, first it has to put address on this bus. Next, as soon as the particular address is selected, the data what is present on that can be read through this data bus, or if the data is present in the processor, I can write into that location from the data bus. The size of the data bus, let's say n bits, means the word length of the processor is n bits. If it is a 32 bits, we'll call it as a 30-bit processor. Now, apart from these two, we also require certain control lines which are generated by most of the times by the processor, but sometimes some signals will also come from the memory. Let's understand these control lines. Let's say I want to write one data, let's say 35, at the location called 2000 in the memory. Then what I will do is I'll put 2000 and the address bus. We will put 35 into the data bus. Now, as soon as we put an address, as soon as put the data, does the memory knows that we have placed the data? No, memory does not know whether you place the data, because why? Even if you are not placed the data, some data is always will be there on the data bus. Either it's all zeros or all ones. So that means that all zeros, all one does not guarantee that always some data is there and always some address will be there. Memory does not know that. You place the new address, you place the new data. So we have to inform the memory by the processor after placing that address in the data that we have placed the data. Now start getting it written inside the memory. We have to inform the memory. That's why one signal called read/write bar is given. Sometimes we use an external logic to convert read and write into separate signals, one read signal and write signal. For all our understanding, in the discussion, we assume that the two separate signals are there, one called read and write. As soon as we generate a write signal, it is like a pulse. We generate a write signal like this. On the write signal, then the memory understands that we have placed an address, we have placed the data, memory takes the data and writes into this one. Similarly, if I generate the signal on the read signal, then memory understands that based on the address what we kept, the data has to be placed in the data bus so that processor can read it. Now, so we have understood read and write the signals. There's another concept is that processor works at a higher speed than the memory. Processor works, let's say, millions of instructions it can execute in a time. But does the memory is the capability to supply the data or consume the data at the speed of the processor? No, memories are very slow compared to the processor. So then what we have to do is, when we want to write 35, 40, 60, let's say 3 data I have to write to the memory. The moment after finish writing 35, can I take the second number and write it immediately? We cannot do it because the previously written data has to be consumed by the memory. That's why all the memory will generate, the chips will generate one signal. So the name of the signal is called memory function complete. So this signal will be generated by the memory chip. Its name is called as memory function complete. So after we write the on data, we will keep watching the signal. Is the memory function complete? Signal is generated by the memory. If the signal is generated, that means that the signal becomes 1. That's an indication to the processor. I can write the next data. So these 3 signals which are essential to communicate between the processor and memory is called as control lines or control bus. So what are those? Read, write, and memory function complete. So overall, the memory and the processor interface require 3 sets of buses: address bus, the data bus, and the control bus. Now, so there is a concept called registers, special registers, which are required to communicate to the memory. So till now, we have understood that there are general purpose registers are there. Programmer can use this register in programming using assembly language. We have used all these instruction registers. These are called general purpose register. And also we have understood a program counter is required to indicate which is the next instruction to be executed. We also understood IR register is an instruction register. As soon as we get the instruction from the memory, we keep in the instruction register, and the control unit based on the instruction register will generate a control signals. And ALU is the one which performs all arithmetic and logical operations. Then what is the purpose of MER and MDR register? We generate an address to the memory in 2 occasions. If at all, if I want to get the instruction of the memory, we take the contents of the program counter. I have to place this contents on the address bus. What is another occasion? If I want to read the data from the memory, not the instruction, data from the memory, then I pick the address from any of these register, pointer register, place the data on the address bus. That means that many of the sources, like a program counter, registers, want to get connected to the address bus, but there is only one address bus is there. To make the one address bus which is present outside the processor get connected to the internal bus, which is the one which connects to different blocks, an interface called MER is provided. MER is nothing but memory address register. It provides an interface between external address bus and internal data bus of the processor. So anything we want to place on the address bus, we have to first bring it to the MER. Through the MER only it's going to get connected to here. MER is a single direction. You can just watch here. It's a one direction because address bus is always one direction. The processor is a master. All other things, memory, peripherals are nothing but like a slaves. So processor is the one which generates an address. So that's why it's called as a one direction address register. So it's always permanently, MER is permanently connected to the address bus. Similarly, the memory is used either to read the data, to write the data, and also to read the instruction also from the memory. So again, different registers are used, want to communicate with the memory, but there should be only one register we should be able to establish the connection. So that is an MDR register, memory data register. It establishes connection between the internal bus and also the connection to the external data bus. Now look at the direction. MDR has got both the direction, because why? I can use the memory to read the data, read the instruction, or write the data. So unlike MER, MDR is a bidirectional register on both the sides. That means that from the register also I can read MDR, from MDR I can read into the register also possible. So when the question is asked, write the connection between the processor and the memory, means you should write this diagram, clearly indicate this is an address bus, data bus, and the control bus. That is the 3 signals, and write MER and MDR. So these are the interface between the memory and the processor. Now let's understand how the processor is designed inside using a single bus organization. Now you can look at the block, what is present inside. All the blocks are connected by only one bus. So if you use one bus to connect all the blocks, we call the organization as a single bus organization. All the blocks together with the single bus and their connections, we use a word called as data path. Data path is the name given to all the connections, single bus on the blocks. So these connections will be called as a data path. Now let's understand how this single bus architecture works inside the processor. Now, so we know that the inside bus is connected to the external bus, external address bus and memory address and data bus, which are connected to the memory. They are connected using MER register and they are connected using a MDR register. We have just now understood. Now just remember that it's a bidirectional on both the sides. Here also it's a bidirectional. So here also it's a bidirectional. MER is a single direction which is used to generate an address bus to the external, this one. Now Program counter is 1, which generates an address for the next instruction to be executed. Now, so whenever we want to perform any operation, so we have to bring the first instruction to the instruction register. So we'll bring the instruction to the instruction register, and then based on the instruction what is available inside the instruction register, the control unit reads the meaning of the instruction and then generate different control signal. These control signals are very important because these are the signals which are the one which controls all the different blocks what is present inside the processor. Now, let's say I want to add the two numbers using this organization, this architecture. Then what we should do is I have to use ALU. Now look at an ALU. Is it possible to get two datas onto this internal bus simultaneously from two registers? Let's say these are the registers. I want to add two numbers which are stored in R0 and R1. So what I can do is I can get one data into the B operand of the ALU. Now, can I get another data from another register into the A operand directly? A operand, we cannot get it because why? The bus is used to fetch only one data at a time. Whenever we have a single bus, if some bus is engaged, see now R0 is sending the data on the bus to the B, I cannot place the data from another register in the bus directly because why? It will overwrite the data on this one. Data will get corrupted and the circuit also get damaged. I cannot do it. So that means that two datas at a time we cannot place in the data bus because the bus is only one bus is there. Then how do we add the two numbers? That is why for that purpose they have provided what's called Y as a temporary register. So what do you mean by temporary register? It is used for internal usage. It is not available for the programmer. Programmer can use only R02 or N-1. Programmer cannot use temporary register. Now what is the purpose of Y here? So before, if I want to add two numbers, what I will do is I'll get the data from one of the register, keep in the Y. So in the next clock cycle, I'll get the data from the R0 and then I'll give an instruction to the ALU to perform the addition. So like this, we can use the Y temperature so that we can supply the two operands required for the ALU. Now, similarly, why Z is required? Whenever we perform arithmetic operation, the Z, that is the data, whatever produced by the ALU, I cannot write immediately to the data bus because why? When we are adding, already one of the number which is there in the bus, other number is applied from the Y. Whatever the answer I get in the same clock cycle, if I write in the bus, it will corrupt the data what is present on the bus already. So that's why. So we can write that answer in the next clock cycle to the place wherever required. Temporarily, I have to store what? In a Z register. So Z register holds the data, holds the answer. In the next clock cycle, from the Z, I can write into any of the register possible. So what is the concept we have to understand from here? Whenever the single bus is there, you cannot do multiple operations simultaneously. We have to do one after the other. We have to do it. So if I want to add the two numbers means first get one of the number into the Y register, keep it ready. Now get the another number into the bus now, perform the addition, keep temporarily the answer in the Z register. Then in the next clock cycle, Z contents I can write into any of the register. So this is a disadvantage of a single bus because only one bus is there. So if I want to do multiple operations, you have to do one after the other. One clock cycle, some operation, next clock cycle, some other operation, other next clock cycle, some other operation I supposed to do it. Okay. Now, so now let's understand the performance or how we can able to use it. Whenever multiple blocks like this, for example, multiple registers are connected to the bus, MDR is connected to the bus, MER is connected to the bus, IR is connected to the bus, so many units are connected to the bus directly. Now, at a time, only one source and one destination should use the bus. So if you directly connect all of these blocks to the bus directly, then what will happen? The data, whether you want or not, every register places the data on the bus, whether you want or not, because you directly connected. Then what will happen? Data get corrupted. That is why every register is connected to the bus with some control. Only if I say yes, the content of the register should be placed on the bus. Otherwise, you should not place it. Similarly, writing also. Only when I want it, the data should go inside the register. For that, some logic is being developed. So what is that? You can look at the controls here, what is provided here. Every register, let's say RI, we have taken it. RI is not connected to the bus directly. They have connected through what is called one control. So this control is called as a buffer. So it's called as a tri-state buffer. What does it mean? That these are nothing but It is nothing but an inverter, but it will not invert it. Like an inverter circuit without an inversion. Normal ICs like an inverter, whatever the logic you 1 and 0, you get some output. Whereas these buffers, tri-state buffers, will have a 3 states. When it is enabled through the control line, whatever the data you give it, it will pass to the output. Whenever it is not enabled, then whatever the input is connected given will not be connected to the output. It will be open up. It will like a open. So that means that it's like an into means it's a disconnect. It's an high impedance state. So most of the ICs or the buffers will have this capability. They're called as tri-state buffer. They will have a normal 0, normal 1, and one more state called as tri-state, high impedance state. So now this is called as a buffer. Why we are using this one? Only when required, I will connect this line to here. If I am not interested, I can disconnect it. How we can disconnect it? By controlling this one. So every register will have a 2 controls. When I want it, I can write into this one by making RIN as 1. So for example, if it is a R1 register, I can say what? R1 in. Whenever R1 in is equal to 1 means the bus is connected to the RI for writing purpose. Similarly, if the register, I want to read from the register, so we have a control called R1 out. Whenever I make R1 out is equal to 1, that means that whatever the data present in the R1, I can read into the bus. So every register will have two controlled buffers there. One for the controlled by in, other controlled by out. So like this facility is there, then only we can able to make what? Multiple blocks communicate over a single bus is possible. Similarly, the Y is a temporary register. I said it's required to hold one of the operand required for the ALU. So it is whenever we require to write into Y, we use what is called Y in. There is no Y out is there. Automatically Y out is connected to the ALU through a multiplexer. So Y multiplexer is required. What is the concept of that one? So let's understand this one. Whenever we fetch the instruction into the processor, the program counter is used indicate from where I have to fetch the instruction from the memory. After I fetch one instruction, we know that in a 32-bit architecture, program counter has to be incremented by 4 to point to the next instruction. That means that every time you finish instruction, program counter has to be incremented by 4. Again, I require some logic to add 4. Instead of using a separate logic to the 4, we have used an ALU to perform what is called as adding the 4. That is why sometimes ALU is used to add 4 to the program counter. Whenever we want to add 4 to the program counter, I use a multiplexer with a constant 4. Constant 4 means what? Adding 4 to the program counter. So there is a line called select line is there. Whenever I say select 4, then 4 comes to the A and the program counter, I bring it to the B so that I can add it. After addition, I can place it back to the program counter. In all other times, we connect Y to the A. So if I don't indicate select 4, always you just assume that Y is connected to the A. That means that Y is connected to the A. For all our discussion, Y is always connected to the A. Only when I say select 4, the constant 4 comes to here so that I can able to add the program counter. Now, so let's come back to here. So that is the meaning of this one here. Now again, Z, so in is available, Z out is also available. So Z in means the whatever the answer generated by the ALU will be written to the Z. When I say Z out is enabled, whatever the data is available in the Z out will go to the bus and go to the destination, whatever required. Now, having understood that, now all the blocks are enabled to the bus or disabled to the bus by our control. Now we will start writing small instructions or order to these blocks. What is the order in which they have to work? Because when you want to execute an instruction, you cannot complete in one clock cycle. You have to do it. First of all, get the data to the ALU, perform the operation, then store it back to the register. Small things you have to do it to get the work done. So we will write now the sequences. So that in the same order they have to do that sequence so that to complete the execution the instruction. Now, so before we move to that sequence writing, so we will see that what is the control provided for the MDR. So as we know that MDR is a bidirectional. When I want to write something into the MDR from the processor side, MDR, so out is used. I'm sorry, MDR in is used. Whenever we want to read from the MDR into the internal bus, we use what is called MDR out. Same another 2 signals controls are provided. When we want to write MDR into the external memory data bus, MDR out is used. MDR out E. You can just see that E is the one which differentiates MDR out and MDR out, normal out with an E. MDR in E means I am reading the data into the MDR. So that means that these are the two controls which are used to connect to the external data bus. These are the two controls which are used to connect to the internal the bus MDR. So it's a bidirectional. We should be very careful when you use which is you are using, either MDR out or MDR out. E we using. E means external bus. So now let's write the sequence. Now first sequence we are writing it. So analyze carefully. You may not follow in the first listening. You have to repeat it. You go through the slides 2-3 times. Write on the paper so that you can get the meaning of it. Now we will write a control sequence for the instruction add R1, R2, R3. Now what is an assumption we made? This instruction machine code is already present in the instruction register. Automatically it has come to the instruction register. It is already there in the instruction register. Now looking at this instruction which is there in the machine code format, the control unit should generate sequence of signals so that execution will be completed. Now what are the sequence you have to give it? Now first of all, so remember I have to do R1, R2, R3. Now I have to give a sequence. How many clock cycle it is required? In each clock cycle, what is supposed to do it. So let's go to the diagram and explain, and let's just come back there. So the instruction name is add R1, R2 and R3. So now look at this diagram here. Now contents of R1 has to be added to the R2 and the answer has to be placed into the R3 register. So what we have to do is R1 contents, first we have to bring it to what? One of the temporary register into the Y register. Then I can read an R2. Then I can perform an operation. Then answer I can keep it in the R3 register. So this same sequence now we have followed here. So first R1 out, Y in. That means that one of the operand which is required for addition, I am keeping in what? Y register. So R1 out means what? Bus can be used for only one operation. So bus is used for only one operation. So what is an operation we are performing? R1 register out means output of the R1 register is connected to the bus now. Because why? R1 out is a signal to a buffer. Whenever you send it the signal, what will happen? R1 is connected to the bus, internal bus. At the same time, now you have placed the data on the bus where the data should go. This is the source. So which is the destination? Y in register. Y in means what? A control given to the buffer. So which is connected to the Y register. So we just, the moment Y in signal means what? It's one clock cycle. We make it what? High. This is also high. When both are high, what will happen? The source gets connected to the destination. Contents of R1 will come to the bus. From the bus, it goes to the Y. So all these things happen in one step. That's what we can call as a one clock cycle. So during this time, I cannot do any other operations, the second and third, because why? The bus is used for only one operation at a time. I can do it. Now I finish the first one. Now R1 has reached Y. Now I have to finish addition. Now for adding it, I require one more operand. What is an operand? R2. Now R2 out means I am connecting the contents of R2 to the bus. And I am making a multiplexer which was available to select either 4 or the Y. I am just making it select Y. That means that the contents of Y has been placed on the one of the operand of the ALU. Now you have to, ALU is capable of doing multiple things: addition, subtraction, multiplication. So we should tell the ALU what operation is supposed to perform. Now I'm telling that perform the add operation. Now at the same time, you can perform the addition. You can store the answer in the Z also. In the lab, you have seen that when you use an adder, as soon as you give the data, immediately you get an output. You don't require another clock cycle. That means that in the same step or in the same clock cycle, I can finish addition and store in the temporary register called Z register. Now during the second clock cycle, what is there in the bus? R2 contents is there in the bus. Already what is stored in the Y is being supplied as one of the operand to the ALU. And ALU contents output I cannot write directly to the bus. That's why Z register is provided. Because why? During the second clock cycle, the bus is occupied by R2 data. So now the moment you finish the second clock cycle, now the answer is in the Z register. Now one clock cycle is completed. Second. Now we'll go to the third clock cycle. Now bus is free. What you can do? The answer is previously stored in the Z register. I open the Z out buffer. I make the R3 open. then what will happen? Z contents will come to the bus, and the bus contents will go to what? R3 for writing. So now this completes the sequence what is required to complete add instruction R1, R2, R3. We will repeat the same thing through the bus here. So now what is the first clock cycle will happen? R1 contents. I think I'll clear the screen if possible. So any way to clear screen? Okay. Mohan, I'm audible?
Yes, sir, you're audible.
Okay. Okay. So now what is the 3 steps required to perform add R1, R2, R3? I'll repeat. So first take the value of R1 register. So place it on the Y. So for that what we do? R1 out, then Y in, control signals will give it. So the data will come to here. Now it's ready. In the second clock cycle, what we do? We will select the multiplexer Y so that the data will come here directly, and the bus is empty now. So what I will do is R1, R2. Now we'll place the data on the R2. As soon as you place the data on the R2, one of the operand of the ALU is always directly connected. You can just see that there is no connection, it's directly connected. Whatever placed in the bus, always it also comes as what? One of the operand for the B. It is directly connected. R1 through Y it has come. R2, I'm just opening the R2, R2 out. Automatically it comes to the bus. The bus is directly connected to the B. It comes here. Now, as soon as you give the data in the second clock cycle, answer will come. So you are enabling the Z for writing and you write it here. So this is in the second clock cycle. Once you have the data in the third clock cycle, the contents of that we write into what? R3 register, we will write it. So these are the 3 clock cycles or 3 steps required to complete add R1, R2, R3. So who will generate all these control signals? The decoder will generate. So how does it knows that? It knows by looking at the instruction. By looking at an instruction, it generates Z out, R out, R in, R out. All the signals will be generated for every clock cycle by this logic. That we will see at the end of the session how we can generate all these signals. So now we have finished control sequence for one instruction. Now let's understand the memory. Now I want to read. I want to memory write. So we will write a control sequence for the instruction involving memory read operation. Okay, we will first finish memory read operation. Assume instruction is already fetched from the memory and stored in the IR. Now we'll understand the logic. Read this instruction properly. What is the meaning of this instruction? Move the contents of memory location whose address is stored in R1 to a register called R2. I'll repeat. Read the contents of memory location whose address is stored in register R1 and then move the data to the R2. I want to complete this operation. In the previous case, no memory was involved. Once the instruction is brought to the processor, R1 was inside, R2 was inside, R3 was inside. Look at this instruction now. Now you cannot move this data to the R2 because why? This data is not inside the processor. It is there outside whose address is indicated by R1. So first I should get the data from the memory, then only I can able to move it. So this type of operation is called as memory read operation. So previously what operation we done? Addition operation or arithmetic operation we have done it. Now we are doing a memory read operation. What is the sequence required? Let's understand the sequences one by one. The first thing, as soon as I have to perform the completion of this instruction, I will look at the first operand. Since it's not available inside the processor, I have to initiate getting the data from the memory. How do you initiate it? First of all, you have to take the address from the register called R1, because which gives the address, and place it in the address bus. Address bus, we know that it's connected by a register called MER register. So take the R1, open the R1 to the bus. So R1 data address will come to the bus. From the bus, make that data goes to the MER register. Now what has happened? As soon as the data comes to the MER in register, output of the MER is always directly connected to the address bus. So what will happen? The address which you are supposed to read from the memory comes to the address bus of the processor. Now the memory will get an address. As I said in the beginning of the lecture, memory does not know whether what operation you have to perform. I should indicate that. That is why a read signal is generated. The moment read signal is generated, memory understand that somebody is requesting the data. It looks at the address bus, what address is placed, from that address it gives the data. Now already we have placed an address, it is there already. So in one clock cycle, this is what all we can do it. Now we'll go to the second clock cycle. Now first clock cycle is finished. Second clock cycle, what is that we have to do it? We will not get the data from the memory immediately, because memory is a slow device. It may take 2 clock cycle, 3, 4, 5 clock cycle, depends upon the speed of the memory. Only after those many clock cycles you get the data. So what should I do it? How do I know that whether memory is ready and has placed the data? That is why this signal called wait for memory function complete. So I should keep on watching the MFC signal generated by the memory. Whenever the signal becomes 1, that means that memory has responded by placing the data on the data bus. As soon as this signal comes, then what I will do is the data what is placed in the memory has to be written to where? Into the MDR register. We know that MDR is connected by the 2 signals. MDR is connected by the 2 signals. You can look at that MDR. Where is my data? Data is coming from the memory from this bus. I should make it write into what? I should write this data into this one. That is why during the second clock cycle itself, I'll make it open and keep it ready for the data to come and sit in the MDR register. That's what we have done here. So MDR in E, I opened it up and keep it ready. So as soon as I get the data, it goes to the MDR register. This is what we can do in the second clock cycle. So after completing this one, then only we enter into the third step. So third step means it may not be the third clock cycle, because during the second step, you may have a multiple clock cycles. You may have a 2, 3, 4. We call every extra clock cycle which is inserted in the second step is called as wait state, W-A-I-T. Wait states means what? It's nothing but a dummy clock cycles which are required to wait for the synchronization between the slow device and the processor. So now after the wait states are completed, then I'll come to the what is called third step. Third step is called as I have the data in the MDR. You can look at here. I have the data in the MDR. I have to write this data to what? The required place. I have to write through this bus, internal bus, and write it to a proper place. So this is what we do in this step. So MDR out means what? The one which is connected to the internal bus. So MDR data is placed where now? On the internal bus. Again, the data on the internal bus, I supposed to write into a particular place where I would write into R2 register. That is why open the R2 register for writing it. So this is what is called as third clock cycle. So here we require 3 clock cycles for the wait stage to do it. So R1 and R2 are the 2 registers involved in this case. So now let's go here and just repeat the same operations one more time. Okay, so now we'll repeat. So what is the first thing we'll do? I have to take the R1 contents, place it on the MDR register, and make address available to the outside. Sorry, it's not MDR register. It has to go to the, one moment, I'll just remove that. Okay, so whatever the register R1 is there, it has to go to the MER register, and that address should come out to outside. So this is the first clock cycle. So R1 out, MDR, MER in, so that address comes here. Then I have to wait for the data coming from the memory, but I'll open the channel here. I'll make it ready. As soon as the data comes from the memory, the data writes here. Then you have to wait for the data to come here. That is a wait for memory function complete. So second clock cycle is completed. Once you have the data here, now what you do? Allow the MDR data to come to the bus and make this bus connected to R2. That means that it goes to the R2 register. So these are the 3 clock cycle what is required to perform the memory read operation. So this is what we have done it here. So now we'll go to the next sequence. So I want to store a word in the memory. In the previous what we have done, memory read operation we have done it. Now we will see what is the sequence required for the memory write operation. So write the control sequence for the memory write operation for the instruction move R2 R1. So let's understand the meaning of this instruction. So what is the meaning of the instruction? What is present in the R2 register? I am writing into the memory location whose address is indicated in the R1 register. So here the second operand is not present inside the processor. The second operand is present inside the memory, but only the reference, that is where is that memory location, is given by the R1 register. Now, so we will assume that the whole of this instruction already present in the instruction register. Now I want to complete the operation. I want to write the sequence. So what is the sequence we supposed to write it now? First, now I have to write some data from the R2 and place in the memory. So the memory location, what is required, is present in the address in the R1 register. So I will take the R1 out and write into the MER in. Then what will happen? The address of the memory location which is there in the R1 will be placed on the address bus through the MER register. R1 is out, internal bus is used, and then I return to the MER. Now the bus contains the address. Now the memory knows that it has got some address on the address bus by using what is called as a write signal. Now as soon as I place an address, I will generate a write signal in the second clock cycle. In the second clock cycle, the memory knows that somebody has placed an address and they issued already the write signal. What does the memory want? Whenever you want to write it, somebody has to give the data. Who has to give the data? Processor has to give it the data. So where is the data we have? It is available in the R2 register. We have it. So along with the write, I'll take the R2 data and place it on the data bus. Data bus is connected through what? MDR register. So I'll make MDR in. So that means that, so in the first clock cycle, we place an address. In the second clock cycle, we give a write signal and place what is the data to be returned to that address. Now, again, the second clock cycle, it's not one clock cycle. Number of wait states will be introduced here. We keep on waiting until it says that it has completed the operation. So we can also write here also what is called wait for memory function complete. We can write it here. So that is what, instead of writing in the second clock cycle, we are writing in the third clock cycle. So in the third clock cycle, whatever the MDR out, which is we have written into the MDR in, now we have opened it up for the data bus. So this has returned into the data bus, extra data bus, and we are waiting for the memory function to complete. So we may feel that we can write this in the second clock cycle, it will finish us, but it cannot happen that, because first I have to place an R2 onto the MDR register. In that clock cycle, I have to finish writing. Then only I have to open the MDR out. I cannot make the MDR in and out in the same clock cycle. That is why in the second clock cycle, we finished writing to the MDR. In the third clock cycle, we open the MDR to the external data bus and wait for the memory function to complete. So once we get this signal, that means that this operation is completed. We can go for the next instruction to be executed. So we have completed arithmetic operation, we completed memory read, and we completed memory write. Now it's a time for us to go to the complete instruction. Now this is a little challenge easier to understand. Let's go step by step. Now write the control sequence for the execution of the complete instruction. This is a full instruction I have to execute now from the beginning. So now always we have to write steps like in English simple language like this. We have to write it before writing the sequence. What are the steps you have to require? Every instruction execution requires multiple steps. What are the first steps in this one? I have to fetch the instruction from the memory. This instruction in machine language format is stored in the memory. In all the previous cases, we assume it's already there in the instruction register. Now we cannot assume. We have to now writing the instruction sequence for the whole instruction. Where is instruction is there? It is there in the memory, which is outside the processor. So what the first job I have to do? Get this instruction into the processor. When I say get inside the processor, where? Inside the instruction register, this has to go and sit. Now, once you get the instruction, then we know that the instruction register gives this knowledge to the control unit. Control unit will read this data, understand, oh, it has to perform. So addition of two numbers. One number is there inside the processor, another number is there in the memory, so that it will fetch the another number which is there in the memory. So that means that fetch the first operand. So we should be very careful here when we write the complete sequence. We should be know that what is the each step performs. So get the second operand, that is one of the operand. Now both the operands are there in the memory after the completion of the step number 2. Now you can complete the addition because the data is there, both the operands are there. Once you finish, you have to keep the answer back into the R1 register. So that means that you have to perform the move operation. So whatever the result generated by the ALU, you have to write into R1. So these are the 4 steps. So let's repeat. The first, I have to get the instruction from the memory into the processor instruction register. That is called as fetch the instruction. Second, read the instruction and just observe, is every operand is there in the memory, is in the CPU or not. If something is missing, just find out what is missing, where it is there, how to get it. In this case, operand is there in the memory, I have to get it first. That is why fetch the first operand which is there from the memory. I finish the sequence for that. Then I have all the data is there inside the CPU. Then perform the operation, the addition you finished up. Then once you finish, you have the result, place it wherever required. I want to move to R1, finish that, do the data transfer, or called the move operation, you perform it. So once we have done all the 4 steps, then start writing the sequences. What is the control sequence required for every operation? Let's do with the fetch the instruction. Now, when I say fetch the instruction, who will generate an address of the instruction? You should always know that it's a program counter. Program counter is the one which generates an address for the instruction to be fetched. If you want to read any data, any other register can generate an address. But if you want to fetch the instruction, only program counter can give the address. That is why PC out. So take the PC out, use the bus, place it in the MER, and the address is placed in the address bus. Now, give the signal read to the memory, telling that I am interested to read instruction from the memory. Now, along with this, we are doing some more operation here. What is this operation we are doing here? Now we know that whenever the program counter shows one instruction address, and as soon as we get that instruction, program counter has to be automatically incremented so that it will point to the next instruction to be executed. So where is the next instruction is there? In a 32-bit architecture, word length, program counter has to be incremented by a value called 4. So by 4, if you increment it, program counter will be ready for fetching the next instruction. Since during this time, the complete bus is free because you got the PC out, MER, and you initiated that operation. During that time, ALU is free. ALU is free. No job is there for the ALU. What we are doing during that time, we are using the ALU to perform what is called addition of the program counter by 4. Because ALU is used for what? Adding the value to the program counter by 4 also. ALU is used to perform other operations also. So how do you get the program counter into the ALU? We know that as soon as the PC out comes and enter to the MER, the same bus is also connected to the ALU. We know that all the registers, when they open up and connect to the bus, means one of the operand in the ALU is directly connected to what? Directly connected to the bus. So that the PC which is there in the bus automatically will be there on the ALU, one of the operand. Now, when I say select 4, the multiplexer which is connected to the ALU of the operand enables the 4 to come to the ALU. Now, I will initiate a signal called add to the ALU. Then as soon as you addition, I want to keep in the Z in. So I'll explain this with reference to the diagram. Okay. So now look at here. So in this case, now I am just telling you that in the first clock cycle, we have to fetch the instruction from the memory. At the same time, I want to use the ALU to perform addition of the program counter. So what we do? First, I'll take the program counter. Through the bus, I am writing the ALU register. Now address is there to the memory. I'll initiate read operation. Now this job is done. But look at the ALU. ALU is free now. What I can do is the program counter value which is placed on the data bus is already connected and available here. It's already available here. Now what I can do is I have to bring the 4 to this place. I have to bring the 4 to here. How do you bring the 4 to here? By giving a select signal. When I say select 4, the 4 comes here. The data of the PC which is going outside here, it's also coming here. I will just indicate an add instruction to the ALU. Then I'll open up Z for writing it. That means that along with generating the PC onto the address bus, you finish the program counter adding by 4 so that it will be ready for the next instruction fetching. Now, where is your program counter content at the end of the first clock cycle? It is there in the Z register. Now, in the second clock cycle, whatever there in the Z, write it back to the program counter. So program counter will be ready for the next instruction fetching. So now let's go back to the Okay. So first clock cycle we have understood. We have done that operation. Second clock cycle. What is there in the Z? That is incremented program counter. Write it back to the program counter. So program counter is ready. Now at the same time, so this Y in one extra thing is there. We will discuss this in the next session. Next session in the sense when we discuss other instruction. At the moment you assume that it's required. We will discuss this later. Now wait for the memory function complete. Wait for the instruction to arrive into the processor. Now, so once instruction comes into the processor, so from where does it comes? From the external data bus. Now it is there in the MDR register. Now make the MDR out so that whatever there in the MDR, that is nothing but an instruction. Take the data, use the processor bus and write into very important register called IR register, instruction register. Because why? Now what you got through the program counter address is an instruction. It is not the data or something else. So whenever instruction comes, you have to write into what register? Always instruction register. So that is why third clock cycle, the instruction which has arrived to the from the external memory to the MDR, we opening it up and just open the IR register so that instruction sits in the IR register. So now after the first 3 clock cycle, we completed fetch instruction. If in the exam the question is asked, write the control sequence for fetching the instruction means you have to write 1, 2, 3 and stop it. Now we are continuing now because why? We have to complete this instruction execution now. Now you got the complete machine code of this instruction, binary format is sitting in the IR register. Now the control in it, which is the one which is connected to IR, looks at this instruction, understand. Oh, there is a requirement of one more operand. I have to read from a outside with the help of R3. Now what happens in the fourth clock cycle? Memory read starts. Now reading from where? With the help of R3. Now take the R3 which contains an address, place it in the MER register through that MER and initiate a read to the memory. See, look at this. In the fourth clock cycle, we are placing the R3 data onto the address bus. So through the MER register and initiating read signal. In the next clock cycle, so the whatever the data which is available on the data bus, that is which is available on the address bus, is nothing but R3 contents are placed on the address bus. You have initiated the operation for reading it, but during that time your bus is empty. That in the sense you have finished this operation, now in the next clock cycle, anyway you have to wait for what is called wait for memory function. You have to wait till you get the data from the memory. But what we can do is parallelly, since the bus is empty in the fifth clock cycle, we are adding R1 and another operand, because I cannot put both the operands on the data bus directly. So since the bus is free here, get another operand from R1, keep it in the Y register. Y is the temporary register. So because we know that when we perform an ALU, we require one of the operand in the Y register, another operand in the bus, we have to bring it directly. Since another data still is coming, I'm waiting for the data which is coming from the memory. At that time, I am writing the R1 contents, which is nothing but what? Another operand into the Y register, which supplies one of the operand to the ALU. Now, in the fifth clock cycle, we have completed. That means that memory has given the data present in the memory location pointed by R3. I got the data. Already one of the operand is there in the Y register. So now what I will do is, Y means it's automatically what? It's just through the multiplexer. I say select Y means R1 which is there in the Y register will come to the ALU. Now the new data which has come from the memory location is there in the MDR register. I'll just open it up. Now through the MDR it comes to the another operand of the ALU. That means it comes to the bus and it's available as another operand to the ALU. Now give the instruction add and then write into the ZIN. So in the sixth clock cycle, we completed addition of R1 and another operand which was there in the memory. We finished it. So where is the result? Is in the ZIN register. Open up the Z out and you are supposed to write into the R1. So make it R1 available for reading and then stops the execution.
Hello.
So these are the 7 steps. What is required to complete? Fetch the instruction, fetch the operand, perform the addition and move the data into the destination. So only if you write 1 or 2 times on the paper, you get the complete knowledge. Keep always the full diagram on the left side and then write the sequence. It's easy to follow it up. So now we'll go to the next one. So write the control sequence for the execution of the complete instruction add R2 and the R1. So here it's a very simple operation. We can easily follow here. So first is what? I have to get the instruction from the memory. Then I have to perform the addition using the ALU. So then whatever the result comes from the ALU, I have to move it to the R1. So you can easily follow now. So first get the instruction, same thing. PC out, MER in, read, select 4, add, Z in. So make the program counter. The first 3 instruction, no change is there. You can look at the first 3 instruction called memory fetch the instruction from the memory. This is same thing. It's the same as the previous case. Now only here in the fourth clock cycle. So R1, I am just taking one of the operand and putting into Y, because one of the operand has to be kept in the Y before we do the operation. Then in the fifth clock cycle, already enable the Y, get the Y data into the one of the operand of the ALU, make another operand comes to the ALU by R2 out through the bus, perform the add, stored in the Z register. In the last clock cycle, whatever there in the Z, write back to the R1 and the end. So like this, write the steps first and then write the sequence. Now let's execute now branch instruction. So what is the branch instruction? Branch instruction execution or writing the sequence for a branch instruction is little different. So let's understand. There are two types of branch instructions. Conditional branch, unconditional branch. Unconditional branch means when I say branch loop, there is no conflict. You have to execute the branch instruction because condition is not there. Branch loop means it will 100% will branch to the loop label. When I say branch less than 0 loop, then only when the based on the 0 or carry flag, when the previous answer is less than 0, then only I will branch. So whenever we execute a branch instruction, just find out, is it a conditional branch or unconditional branch instruction? Now, in case of unconditional branch instruction, we have to understand that the branch instruction contains two information. One is the opcode, which saying that branch instruction. Other is called as offset value called X. X means it indicates where is the new place where I have to shift my program counter to the new place, because program counter is always sequencing. When I say branch, you're stopping that place, you're going to the other place. So a branch instruction replaces the contents of a program counter with a branch target address, which is usually obtained by adding an offset given to the branch instruction. In the last session, we understood there is a what is called relative addressing mode is there. Relative addressing mode means you are adding something to the program counter and make the program counter point to the new place where you're supposed to branch it. That means that whatever the value specified inside the branch instruction has got the two components. One is opcode, other is what? Offset value. Let's say offset value is 100. 100 does not indicate you have to branch to the location called 100. 100 says that you have to branch to the location whose address is 100 bytes plus program counter or 100 bytes minus program counter. That means that always when we use a word called offset means that it does not indicate the full address. It only says that from the program counter how far you have to go so that you can branch to that location. So whatever specified as a part of the branch instruction, we take that, add to the program counter so that I can get the new address. That is an address I supposed to branch in the branch instruction. So the offset X is usually difference between the branch target address and the address immediately following the branch instruction. So that means that is the offset. That is how much we have to branch. Now, so let's write the control sequence for the unconditional branch instruction first. So what is the first thing we have to do it? So first I have to get the branch instruction into the processor. The first 3 steps are same, no change is there. So as usual, so use a program counter, generate an address, get the instruction into the processor. Only thing here is this is the one is we have not explained here. Always in all the instruction fetch we were writing this. What is this is required? Why this is required? Why in program counter? Sometimes in case of a branch instruction is used for the addition of an offset value. So whenever we access the program counter, in this case program counter, I am incrementing by 4, I am writing back into the program counter. That means that what is the second step is doing? We are adding the program counter and keeping the value of the program counter, new value into the program counter. At the same time, the program counter value, I am also writing into the Y register. Why it is required? It's not required in all the cases, but in some instructions like branch instructions or some other instructions where the program counter uses a reference to go to the other place, I am keeping it ready in the Y register. So that means that in the previous instructions, whatever we studied, there was no use of this one. Even though we are writing the Y, it was not used. But in this case, it's of use, because why? The program counter itself is used to add an offset value here. So when I want to add something to the program counter, how do I add it? Using an ALU. So what does an ALU require? ALU, one of the operands should be program counter. Another value is what? Offset value. So that's what we're doing it. So when I say Y in, the new value of the program counter, I'm keeping it in the Y register so that I can supply that as one of the operand to the ALU operation. Now, I have finished the instruction fetch using the 1, 2, 3 clock cycle. Then I'll start the fourth. So when I say fourth, what does it mean? That instruction has come and sitting in the instruction register now. Now control it looks at that instruction. Control it knows that, oh, it's an unconditional branch instruction. So the moment control it notes that it's an unconditional branch instruction, it knows that there is an offset value called X is there in that instruction. I have to extract it. So this value will be extracted from the instruction register. So offset field of the instruction register will be extracted and outputted on the bus. Since whatever you output on the bus, it comes as one of the operand for the ALU. I am just doing what operation? Add operation. Because why? Already one of the operand is there in the Y in. So the moment I can also write here select Y. So it's not there, we can write, you can add it here, select Y. So when I say select Y, the Y, which is nothing but the program counter, has come, and also you place an offset, then you are adding and Z into this one. That means that, so if you write the picture like this, if let's say this is an ALU, one of the operand is what? Program counter. Why you got the program counter? Because you place the program counter value in the Y in here, so that you can add select here, so that what will happen? The one of the operand here. What is another operand? Other operand comes from the instruction register itself. This is your IR. So IR contains an instruction. In this instruction, the part of the data is what? The offset value. Let's say X is an offset value. So which is being picked up here and placed here. Now what has happened? Now new program counter value will be generated. This value is the one which indicates what is the next address where I have to branch it. Because when you change program counter, you branch to the new address. So that's what's happened here. So Z out, we are writing it to what? Into the program counter, the new address, and then the end. So this is how a branch instructions are getting executed inside the processor. Now let's go to the next one. Control sequence for conditional branch instruction. Branch less than 0. Here the first three is same thing. No change is there. Only the fourth there is a difference is there. Why difference? Here 100% branching will happen in the fourth state. Because why? It's unconditional. In a conditional branch, there is no guarantee. That means that this may execute. Yes or no? This will execute, but the fifth is not guaranteed. Here what? The fifth is always will execute. Because why? You are loading the new value into the program counter. Because why? It's an unconditional branch. Here the fifth will not execute if the condition is not met. Now what is the condition we are seeing? Branch less than 0. That means that whenever it's less than 0 means what? Answer is negative. When the answer is negative, n flag is 1. So n is equal to 1 means, what does it mean? That is less than 0, I have to execute what? The fifth step. If it is n is equal to 0 means condition is not satisfied, I have to stop at this point itself. That means that fifth is an optional here. Depends upon the flag value. If the flag is not satisfied, it stops at this place itself. There you can just look at that. There is a two end is there. One end, there's another end is there. It may stop here or it may stop here. So that is the meaning of what is called as a branch instruction with a condition, branch instruction without a uncondition. Am I audible? Mohan? Any student? Am I audible?
Yes, sir. Audible, sir.
Okay. So now we'll go to the last session of this, the process design. Usually, the single bus-based process are not used nowadays. You take any processor nowadays, multiple buses are there, which will connect all the different blocks what is present inside the processor. Why multiple buses are required? When the buses are many, the number of clock cycles required to perform one operation will be less. So you can just look at the meaning of that here. allow the contents of two different registers to be accessed simultaneously and have their contents placed in the buses AB. You can look at the register file here. Register file means register file is a word we use for the collection of all the registers. See, now three buses are there. One bus A, the bus B, and the bus C. So all three buses are used to execute the instructions. In a previous case, when there is only one bus is there, it was not possible to put the data into the ALU simultaneously, because why? Only one bus is there. I'll just get one, put in the Y temporary register, then they get other one, I'll place it, I'll add it. There was a temporary registers was required, Y and Z. Look at here, there is no Y and Z here. Because why? It is not required now because multiple buses are there. That is the one advantage. Now if I want to read the contents of a register, I can read how many? I can read two at a time. So one of the register I can get into what? The bus A I can get it. Another register I can get into what? The bus B. So at a time I can read two register contents and place it in the buses. Now, since you are able to place two operands in the buses, at a time you are able to connect what? Two operands on directly onto the ALU. See, you can place one operand, you can place another operand directly. Now, so you don't wait for one more clock cycle. In the same clock cycle, I can place both. Now, at the same time, whatever the result generated by the ALU, since one more bus is there, I can take the result, I can write into the register simultaneously. That means that at a time, I can take out two operands from the register. Same clock cycle, I can perform the addition. In the same clock cycle, I can write back into the register. Because why? Register file is connected to three buses. Bus A, bus B, bus C. All are different. So in one clock cycle, add the two registers, place the answer into another register can be completed. This is an advantage of a three buses architecture. Now, in the earlier case, ALU was used to add 4 to the program counter. Now, to reduce the burden on the ALU and to make it effective, so more to increase the throughput, they have provided a separate incrementer to the program counter. Program counter will be incremented by 4 by using another logic called incrementer. They don't use ALU in this case. Now, so now I'll ask the simple question. Just think at the diagram and you can just guess what is an answer. Now, I want to pass the contents of one register to another register. How we can do here? I want to pass the contents of R1 register to the another register called R2. So look at the screen and just guess what is the way we can able to do it. Now R1 is here, R2 is here. Since R1 is connected to the bus A and this is connected to the bus B and this is a bus C, no way you can move the data from one register to another register is possible. See, look at that. Because bus A is not connected to the bus C. Bus B is not connected to the bus C anywhere. So even though you can bring the contents of one register and place it in the bus B, but what is the way to get this data into another bus? How do you get it? There is no connection is here. So in such cases, in three bus architecture, ALU is the way to move the data from one bus to the other bus. This is used. So this is called no operation. That means that no operation is performed by ALU. ALU is just work as a channel to take the data and pass it to the other bus. So this is one of the special feature of the three bus architecture. You can just read it here. ALU simply passes one of its two input operands unmodified to the bus C. So we will call as a one operation that one. So no operation is performed, just use as a channel to pass either bus A, bus B data to the bus C. Now, so using this bus architecture, now we will write one control sequence. So write the control sequence for add R4, R5, R6 for the three bus organization. We can see that. See, the number of clock cycles has reduced now. First, get the instruction from the memory. What is the way? PC out. Place the contents of the program counter on the address bus. R is equal to B. This is nothing but dummy operation using the ALU to pass the data from one bus to the other bus. R is equal to B. What does it mean that? Look at here. This is the R. R is nothing but output of an ALU. What is the B? B is the bus. The moment PC is out means the data of the PC comes to where? The bus B. Now I have to bring from the bus B to the MER register, because MER register is connected to what? Bus C. So what is an operation? PC out, use the ALU to place the data from B to R and then to the MER register. So it comes, dummy operation, it comes like this. So that is the sequence we have said. PC out, R is equal to B. R is equal to means copy the contents of the bus B to the ALU output R. That is nothing but bus C. R is equal to B means it's nothing but C is equal to B bus. So we have finished the operation. Now open the MER for writing the contents of the program counter, initiate the read operation and increment PC. Increment PC is one step sufficient because why? The hardware which you use to increment is different one. So now you finished sending the address. Now wait for the memory to complete the reading the instruction from the memory. Once the instruction has come, take that instruction which is there in the MDR register. Again, use the bus. The contents of the B bus has to be written to what? R, and IR should be open. So just see that MDR is this is the register MDR. You read from the MDR register into the B bus, and from the B bus use an ALU and write into what is called as instruction register. Instruction is here. So take MDR, use the bus and write into instruction register. This is what we have done here. So the second step is, so MDR out, use the bus to copy from one bus to the other bus and write in the IR. So we finished the instruction execution. Now last step. Now this is the beauty of this 3-bus architecture. It's a one clock cycle. Place the R4 on the bus A, out A, R5 out B. Place the R5 on the bus B. So one bus contains R1 operand, other bus contains a R5 operand, B bus. Now select the A. So we have provided what is called as here adding the constant 4. The why this is required whenever we want to increment the pointers. So we know that pointers are incremented many times when we use indirect addressing mode, when we want to do a looping. So at that time it's used in this case. So now, so place the 2 operands and the 2 buses, select the A. So then perform the add operation. Then at the same time, write into the destination register, that is R6 and end it. See that all the operations, once the instruction is there inside the processor, we have completed one clock cycle. So take the R4, R5, place in the buses, perform the addition, place the result into the R6, everything completed. So this is how 3-bus organization is effective compared to the single bus organization. This is what sequence you're supposed to write it. Now, so now we have studied everything now. Now it's a time for us to conclude. So before conclusion, now you have seen till now lot of control signals, R1 out, R2 in, MDR in. These are the controls generated by control unit. How does the control unit generate all these signals? What is the way we can design the circuit? So we have understood counters, registers, decoders, encoders, everything. All those concepts are required to design the circuit. Let's see that. To execute instructions, the processor must have some means of generating the control signals. So needed for the proper sequence. 2 categories of designing the control unit is there. One is called hardware control, other is called as a microprogram control. So people design either using a hardware control method or use a microprogram control to design the control unit. So our syllabus, we are restricted to a hardware control. Hardware control system can operate at high speed, but with a less flexibility. As a microprogram control, it takes more time, but it's possible to add new instructions into the system. So let's see that hardware control method. Now look at this diagram. Look at this diagram. We'll understand step by step. First, we'll understand control step counter. So every instruction is a sequence of control signals generated in steps. Every instruction is a sequence of control signals generated in steps, means in different clock cycles. Each step is completed in one clock cycle. A counter is required to keep track of these steps. So that is, a control step counter is used. Each state or count of this counter corresponds to one control step. The step decoder provides separate signal line for each step. So look at the meaning of this one. Now control step counter, let's say, now to execute the complete instruction, 7 steps are required. Now I design the counter for 7 steps. That means that I load into the counter in the beginning. You know that counters can be loaded, parallelly loaded. I can load into this counter, or I can configure this counter work as what? 7 steps. Now, a counter now will count from step 1 to step 7. 1, 2, 3, 4, 5, 6, 7, like that. Every time it generates one count in the binary format. This is nothing but what? 0, 0, 0, 0, 1, 0, 1, 0, like that. In binary format, counter generates an output. But now I should know When it's a 1, when it is 2, when it's 3, I should know that. Why? Because I have to generate different control signals in every step. In a first step or first clock cycle, I have to generate some clock signals. In the second clock cycle, I have to generate some signals. How do I know that? So that I use a decoder. This decoder looks at the combination. If it is 0, 0, 1, that means that, so it is nothing but the first clock cycle. So I will enable T1, I'll generate a T1. If it is 0, 1, 0, counter gives, oh, the decoder knows it is nothing but 0, 1, 0, I have to enable what? T2. That means that as we have studied in the lab, a decoder is a circuit, one of the many signals will be activated. So when the counter generates 1, it generates a 1. When the counter generates a 2, T2 is activated. So like this, one of the many n clock cycles based on the count, one of them will be activated, and that is been fed to the encoder. So we understood the purpose of control step counter. Now let's go to the instruction register. Instruction which has been brought from outside is kept in the instruction register. How many instructions will be supported? Let's say 6 bits are available to represent an opcode. How many instructions? 2 to the power of 6. So that means that 64 instructions are possible in the instruction register. For every instruction, one line is activated. So that means that every instruction, whatever the instruction you give it, that is 6 bits are there. Those 6 bits are, let's say, represented, and it has come to the instruction decoder. Now, instruction decoder decodes the 6 bits and generates 64 output signal if the 6 bits are there. That means that any one of this signal will be activated based on the combination of the instruction register. For example, if 000 is an add instruction, that means that only this pin is activated. If 010 is, let's say it's a 2, it's nothing but subtraction instruction, then the signal is activated. Now instruction decoder helps us to identify which is the instruction we are supposed to execute now. Step counter indicates which is the clock cycle we are executing. Is the first clock cycle or second clock cycle? With the help of instruction, what instruction? With the help of what clock cycle and external inputs like flags and interrupts, the encoder takes a decision what signal has to be generated output of it. That is what the encoder will do. Encoder get the information from the clock cycle counter, from the instruction decoder, from the read, write, and all the signals, what is external inputs available, and also the interrupts. And based on that, based on the flags also, it generates the signals. So one example is given, Zin. How the Zin signal is generated by the encoder? Zin equals T1 plus T6 dot add plus T4 dot BR plus extra. This signal is asserted or generated during the time slot T1, the first step. So for all instruction, during the T6 for an add instruction, during T4 for unconditional branch instruction, and so on. So based on previous discussion, we know that Zin has to be generated in the first clock cycle. At the same time, Zin has to be generated in the 6th clock cycle for add instruction. Zin is also to be generated what? In the 4th clock cycle for a branch instruction. Like this, we have to write an expression. The encoder contains what? A circuit for Z1. So that means that encoder contains one circuit for the Z-in. Similarly, encoder contains one circuit for the R1 in. Like that, encoder contains lot of circuits which generates every control signal. That is a combination of encoder. So with the help of encoder, decoder, counter, whatever we studied from the unit 1 to the unit 4, all the concepts are required to build control unit. This is how the control units are designed using what called hardware control. Here everything is fixed, you cannot change it. In case of a micro program control, instead of using hardware, we write small micro programs for every instruction, store them in the control, in the inside memory. So there is a micro program counter is there. Here everything is nothing but what? Small program for every instruction. Anyway, this is not there in the syllabus, so I'm not focusing much on this. Just remember that instead of hardware, every instruction nothing but what micro program is there, that is stored in the inside the processor, inside memory, microcode memory. So that is used to generate the sequences. Here everything is a hardwired control. So this completes the processor design of the unit 5. Please go through that and make sure that you can able to write the sequences for the different instructions what is given in the material. So the reference is Hammarskjöld book we have taken for describing all those things. Mohan?
Yes, sir.
Recording stop.
Okay, sir.